lectures on the cloud that I'm just gonna post, as you know, the lectures, the tutorials on the link on the Schoology. And now it seems that we are ready. Let's get started. I'm just gonna open my whiteboard. Then now we are getting ready to get going. Okay, guys, please listen to this tutorial because this one you are just going to expand on the thing that you learned today to move on and make some, I should say, predictive models on your own. Okay, let's get started. Okay. Yesterday, when we finished our lab sessions, we noticed that when we plotted the errors or the residuals from, I should say, from our model, we notice that there is a kind of a pattern between the residuals which we just made them. Okay, now in order to, I should say, in order to improve our model, we go to the higher level of the polynomials. Because based on the thing that you learned on the math sessions that we have talked from the sessions before, you have seen that if you come to choose a single variable x, and you say that you want to transform this single variable x with a polynomials, you saw that actually the general format of a polynomial is going to be this: an x to the power n plus a coefficient an minus n, which is corresponding to power n minus 1 of the variables, plus it goes to all the way to a2 x2 plus a1. Let me take this one off. a1 x1 plus a naught. That's, I can just write x naught x to the power 0, which you know that because x to the power 0 is essentially 1, normally we avoid writing that term and we just leave a naught as a kind of an intercept, and it was a thing that we talked about, that I should say, when we were looking at the concepts of the polynomials. We saw that we think of the intercepts that we have: an minus 1, a2, a1, and a naught. They all have to be real numbers in order to define f of x as a polynomial. And also, we said that the highest power of the n, when we arrange the terms, each individual of those terms in a descending order, that we just start from n, then we go to n minus 1, then we go all the way to 2 and 1, and essentially the next one, which is x naught, which is 0. Then you see that the highest power, it defines the degree of the polynomials that we talked about before. And however, we said that also we name an as a leading coefficient because it comes as a coefficient of the highest power of our polynomials. It was essentially the review of the things that we taught, and that was when we talked about a polynomial of a single variable functions of the x. However, we put all these concepts into an action. We said that we can define in our Cartesian coordinate which it represents, I should say, it represents, for example, at the x coordinate, we do not, sometimes what we have done in the math is that we think of the horizontal axis as x. We said that we can have an interpretation of the x in a way that x can represent the weight. For example, 56 in pounds. And the y-axis, we said that we can have an interpretation of the y as, for example, the height. That's the thing which we have never seen that before. Because when we were talking about the functions, we had their abstract definitions of the x and y. We were looking as a x as a variable, independent variable, and as y as an, let's say, dependent variable. But we saw that we can assign different interpretation to each one. And based on the thing that we saw, I looked the points as the star. We saw that, for example, each star, if defines a point, we can come here and say that we can, in that sense, we see that, for example, we try to fit polynomials for these points. They are scattered on the Cartesian coordinates. On the thing that we did yesterday, we fitted that based on a simple line. We said that in the simplest case that we did, we said that we design it in like that. We say that the y, which is height, is going to be a function of a times x plus b. In a sense that, as you remember, as what we talked, we said that y is the height, x is the weight, and we were wondering how much is going to be a, how much is going to be the b, and that's the thing that we designed it in a simple formula by using LM function in R. We said that, in a sense, we said that height is going to be a function of weight However, our functions was linear because we had one slope as a coefficient for the weight and we had one intercept. That was the thing which we did a couple of days ago. And we saw that because of the error, when we plot the residuals, we see a kind of a simple pattern. It seems that we can just expand from this model and we introduce the model in a different way. In a different way, as if that I can just write functions like that. I go to the second order polynomials. Because on the first one, you notice that the order of the polynomials that you have is simply 1. Now I just want to introduce the polynomials of degree 2. What is a polynomial of degree 2? We know that it's going to be this. It's going to be f of x equals to a2 x squared plus a1 x to the power 1 plus a naught. This is what we call polynomial of degree 2 because we see that the highest power is a2. And we notice also in our case we have 3 coefficients which they are all real numbers. Now, what happens? How should I interpret that in the case of the women datasets that we had? We can write it in a sense like that. We say that, okay, the height, it can be a function of the weight, but in a sense like that. I say weight, and as weight is like the x variables for my analysis, I call weight, it goes to the power 2. I know also it comes with a variable as a slope, which I call that a sub index 2. Then it goes again plus, I have weight. But here the power of the weight is going to be 1. And I know that I have another slope for that. It's going to be a1. Plus, I know that I should also introduce an intercept, which I call that a naught. That's essentially what we are going to do today. We are just going to move away from the model that we had because we saw that this model is not going to be a good representation for our model, because we had a pattern of the errors when we had a diagnostic of our model. And then what we are gonna do, we are just gonna come to stick with this model, which it shows that the height is gonna be a function of the weight, but a polynomial of degree 2. This is what we are gonna do right now here. Okay, before we just move on to, I should say, to our slide, I'm just gonna go to, I wish if I had some more space here, but I'm just gonna write it here at the very bottom of the things which I have done. Guys, look at that. When we just go to the R, in the R, you know that you need a formula in order to just put that in the LM functions that we work with. Still, we are going to use the LM function. But in order to just go to just work with that, I'm just going to show you how we just write the polynomials in our, I should say, R session. You know that in the R, you do not write, I should say, the coefficients A2, A1, and A0 are not explicitly shown. You saw that on the R, we just write it like that. We say that the height you see that you just write the height. It's gonna, the thing which I'm writing is gonna be somehow the syntaxes that you have to use when we just go to our modeling. We saw the height, we put the tilde, which it means that this is stochastically is gonna be related to our height. For the height, when we say that the height is gonna be to the power 2, you notice that we just put this sign, which is, I should say, the power. However, when we just put that in parentheses, we put the I before that. You are going to see that when we do that in the R. Then you see that the slope, the coefficients, the varying coefficients of A2 is not shown explicitly when we run a regression analysis in R. But because I have the power 2, I use the power 2. However, I put the I next to that. It shows the R that we are just using with this data frame, which is gone to the power 2. Plus, oh, sorry, it should be weight, not height. Sorry, I do not know why did I put weight, because we are working with the weights as our variables. It goes weight to the power 2. Plus also weight, which is power 1. And you see that A1 again is not explicitly shown, and A0 also it's not explicitly shown. Then these lines which I have shown, the first line which I have A2, A1, A0 is what we express that in the mathematical language, but the one which we have, I should say at the bottom, the one which I showed that with the heart sign, it's the translation of what I have expressed that in the math into the languaging program of the R in order to find these intercepts. I'm just going to remind you again, when we just go to R, all the purpose which we have is to find a value for A1, A2, and A0. Okay. It seems that that's going to be all the tutorials that we need before we just move on to present the models that we have. Any questions, guys?
No.
Everyone is fine?
Yes.
Awesome. Okay, let me open also my R Studio session. Okay, let me stop sharing, I should say, and I share my R screen, R Studio session with you. Hold on a second, please. opening my R. Then we can just move on to our session. Okay, now I have R open. Let me share my screen. Okay. Okay, everybody sees my screen now?
Yes.
Okay. These are the things that we did, and I hope that you, by now, you can just, you know how to just get the access to the data sets that you have, get the access to the code which we just wrote yesterday. You simply go to the file, you just go simply to just open file, then you open the file, search for the folder that you have created and saved your initial scripts. Then open that and you see the file is back ready. Everyone has the file ready for yourself?
Yes.
Yes? Okay. Now, what we did, we just extracted the data, we checked the structure of the data, we designed, I should say, two objects, which it was the extractions of the height and weight of the 15 women which we had. We stored them into an object as this is called heights and weights. We also, the thing that we did, we just came to plot the numbers. And also the thing which I just want to add here, it's going to be another line of the codes, which is going to be this one. We can also add this line of code in order to index the women. But what do I mean by indexing the woman? Look at the things which I have done. It comes right away after the plot format, which it's written as a text. You can extract the weight as the weight. Look at that. You can also write it like that. You do not need to just the weight I have written. You can just write the weights as an object which you have created when you extracted the weight on the top, or you can just go ahead and write weight woman $ weight. Both of them should be fine. And for the height also, you write it like as the objects which we have created, and it's going to be the heights. You see that the text which I have created here as a command, it goes in harmony with the thing which I have plotted on the top. If I have started with the weight on the x-axis, on the text command, I write the weights, and the y, I write the heights. But the other thing which is going to be different is going to be this. You just write row.names and parentheses. You just put the name of the woman. And these two other things which I have written, it's essentially, it's going to be some variations of how do I just want the fonts of the name should be. And if I execute this, and if you look at the plots which I have done, if I zoom the plots which I have done, you see that for each, I should say, for each woman sets which I had, for example, woman number 1 or woman number 2, all the way going to the 15, and next to each dot, I have a name, a number which is tagged. If I had the name of these women in my initial data sets, I should have had their names instead of the number to be shown. For example, if I had the first woman, her name was Jessica, then I had in red fonts, I had the small name which is printed as a Jessica, and it goes all the way, for example, Jessica, Stephanie, Claudia, and goes all the way. And that's the way which you can keep track of the points on your plot. It's not essential for you to do that, but I just wanted to just give that to you. And also I can just change the color of my data to blue. And you see that we can have, I should say, these formats of the data. It's more like the preference that you have, but we can change the colors as the way it is, but it is somehow kind of a manipulations of the plot that you make. Okay. And now, the thing that we did, we just did the linear model. Yesterday, we run a summary, and also we plotted, I should say, the residuals, and that's where we thought that, okay, the model may be drawn in a way that it can be fitted more better in a polynomial format. Okay, and now the new session starts right now. I say that fitting the model based on a polynomial of degree 2. And that's the thing which I want to do right now. Okay, if I want to move on to fit the model based on the polynomial of degree 2, I'm just going to use the LM function. The LM function, as you see, if you're working with the RStudio, you see that a help menu just pops up on top of the mouse cursor. You see that it says that the LM. I think, Laura, that's the only difference that you may have with the R. You do not have the help menu opens on top of the function. But if you want to see how to get the help for the LM function, you always remember you type the help command, and inside the parentheses, you type the name of the object that you are interested to know more. And I just write help parentheses LM, and when I click enter, click Control Enter, at the same time, I see on the help tab, I have the help. And for the people who are using the R, they have a new browser opens in the Google Chrome or Windows Explorer or anything like that. Okay. Now, I'm just going to come here to fit the model. In order to fit the model based on the polynomial of degree 2, we know the polynomials. We have worked on those polynomials a lot in the Math Advanced Functions 12. Let's try to put them into the action. The first thing which I'm just going to do, I'm just going to go to the help session to see. I know a description of the linear model, which it says that the LM function is used to fit linear models. It can be used to carry out regression, and I do not continue further. I just go to the usage section. The usage section, it shows the command. It shows that LM as, let's say, as a formula, it's written, and it goes, for example, the first thing which I have to put inside the function as the first argument is going to be the formula. Then that's what I'm going to do. I come here, I type the formula, but formula, I say that it's going to be equal the thing which I'm going to do. The variable which I have as an x, which I want to, as a y, which I want to make a kind of a prediction based on the x, if I go back to plot this function, which I did, you see that the y-axis for me is the heights, and the x-axis is going to be the weights. Then my y is going to be the heights. I come here, and I say heights. I press the tilde sign. That's the symbol, the syntax that we use in R and even in Python when we just want to fit the models based on that. I'm going to go back again to the help menu. And the formula which I'm just going to write is going to be this. I say that the help tilde, and it's going to be expressed in terms of the weights. I'm just going to write weights. It's going to be my first coefficients plus, I'm just going to write let me go back to weights. But I know that it has to go to the power 2 in the model, which I'm just going to express that. It has to go to the power 2. Then I just take it to the power 2. Then I know that before, as I showed that on the tutorial, I have to type a capital I, which it shows to the R, languaging session, that the thing which we are going to do is essentially, it is a data frame that it's going to the power 2. Okay. And now you saw that the slope, which it was supposed to be A2, and the slope A1 here, and the intercepts A0, they are not shown. I'm just gonna, when I'm done with the formula, on the help menu, you see that when you are done with the formula, you have to put a comma there. You can continue typing in front. Then I'm just gonna press, go with the next option. I just go with the data, because it's going to be the second argument which I'm just going to put inside the formula which I have. Then I'm just going to put the data, and the data which I'm going to use. What is that? The data is the woman data set. And now I should be totally fine with the first two arguments in the fitting a linear model function. Then when everything is done, I'm just going to press Control Enter, and I see the model is generated here. When you look at the, I should say, the console of your model, you see that first of all, you have the call. The call, again, it reprints the functions that you have had. And also, it comes with the coefficients. The coefficient, it says that the intercept it shows that the intercept is minus 11.74. The slope for the weight, which was A1 in our model, was 0.83. And also A2, the slope for the weight is minus 0.001973. This is the thing. Later, we just come back to store that into an object, then to do some other stuff, to extract some more summaries of it. But at this stage, I want to go back to stop the sharing and go back to, I should say, the model that we had. We expressed that in the whiteboard and show that to you. What does it mean, the model which is going to be there? You see the model that we had, it was expressed in this format. We had the model as the height. We said that it's the functions of the weight to the power 2 plus weight to the power 1. But we had the intercepts A2, we had the intercepts A1, and we had the intercepts A0. Based on the same model, the polynomial that we expressed that in, or I should say on the formula that we had, we extracted that the height is now is a function of, let's say, weight to the power 2 plus weight to the power 1. However, we extracted the A2 is going to be minus 0.0019. I put it to the 2 plus another one which is going to be the intercepts, which is going to be A1, which is going to be 0.83 plus A0. which is going to be minus what was that? Minus 11.74. Which you see that this one is going to represent, I should say, my A2. This one is going to represent my A1. This one is going to represent my A0. Then now we were able to make an inference and estimate based on the ordeal least square method that we talked about that yesterday, the values for these ones. And now I'm going to go back to the R to continue one more further. Then I just give you an assignment to do that yourself. Okay. The thing which I'm going to do, I'm just going to call this one model 2. I'm just going to call that model A. Sorry, model B. Because we had another model before. I'm just going to store that model into this object, and I'm just going to press Control Enter. To store the model inside, I should say, model B, and I see that, again, it's a list of 12 objects. How to extract those objects? You know that the best thing that we do is this. We run the summary, and in the object, I just put model B inside the function. And now, when we run the summary command of the model that we have created, you see that we extract more, I should say, more fundamental descriptive statistics for the model that we have created. We have, as you can see, we have the model. Sorry. You see the model, which is a call for us. It says that we have a polynomial of degree 2 with respect to the weights on our data sets, which is woman. We have the residuals, which is going to be the difference between what you have the actual value of the height and what your model predicts. Similarly, the difference, the minimum of the residual is going to be this. The maximum is going to be this. And you have the coefficients that this is the thing that we are interested in. You see that the intercept is this. The A1 is going to be this, and A2 is going to be this. These are the things that we just extracted when we just run the model before. And the other thing which is important for us at this stage is those stars, which it says that the value which we have made an inference for the square of the weights and the intercepts, they all is denoted by 3 stars, which it means that they are essential to be incorporated into your model. And also, when we come to, I should say, before we finish these tutorials for today, I need 4 minutes before we just go to 9:40. When we go to finish this one, these 3 lines at the end are the most important ones that we can think of it. Okay, look at this one. We talk about the residual standard error. It means that it's going to be the sum of all the squared errors that we talked about that yesterday. It means that when you have the errors, the residuals, which is your prediction, your actual height, you subtract it from the predicted heights from the model, and you take them to the power 2, square them, and you add them all together, the total of all the errors becomes this. Which, if you compare that to the linear model, we are going to do that later, you see that this one is much lower. And also, you come here to see that the multiple R squared, I should say, interpretation. This one, when you get this information, the higher it's going to be much better for you, because this value here shows that the power of, I should say, the model that you have in order to capture all the variation of the heights between the women. And it means that the model which you have here has been able to capture 99% 99.98% information encapsulated by the woman heights and weights in the data, which is a significant number compared to the linear model that we had before. And the last line, we do not talk about that, the F statistics. It's out of the scope of these tutorials, but the p-value of which is going to be less than 5%, it means that the model which you have had here, it's not by accident that you got that number. You can just do this over and over again, but still you get the same level of the significance, you get the same amount of, I should say, for standard errors, and the multiple R squared is going to be the same then. Then you see that this model, it has a better, I should say, description of the data that we had. We have, I should say, because of these two numbers, we look at this model as more something in more favor then. However, guys, any questions so far?
No.
Okay. And now look at that. As a very final step, I'm just going to plot these lines again. I'm just going to back to the plot which I had. I'm going to copy everything and go back to, I should say, the polynomial degree 2 to paste it there. I'm going to plot my data. I'm going to also assign a text to it. And also the thing which I'm going to do, I'm just going to, I should say, come and plot the data sets which I had. First of all, in order to show that the prediction, look at that. I'm just going to go with the lines. The command is going to be the lines. That's what, now I'm just going to plot the fitted model then. I'm just going to go with the lines. Then I'm just going to go with the heights. And also, I'm just going to go, heights is the actual value. I'm just going to go with the prediction of my values. You have seen the prediction before, how to get that. We saw that if we just go with the fitted, which is going to be, I should say, the fitted is essentially a line that we just used that before to extract the predicted values from the model that we fit. You remember from yesterday that when we just go with the name of the objects as a model that we have created, it gives us our prediction of the models. And now if I just come here, put that inside the parentheses, I can just say that here as I call that, let's say, pred y, store that into this object by saying that I have created a vector which essentially it's the prediction of the heights of the American woman, which I have done. Now, either you can just copy paste the whole thing into the second argument of the lines plot, or you can just write pred underscore y. It doesn't make a difference at all. But as we have just stored that into the new object, I said that the pred y, which I created the pred y on the top line over there. This is essentially going to be the prediction of the height. Then what this model does is going to come here to plot the actual heights of the women with respect to the prediction of the heights which I have from the model which I have. I'm just going to press Control Enter to execute the line. And let me see why nothing comes up. I think this is one of the times that my R Studio is, as before, as you have seen, it just stops working. I don't know why. The code is executed there, but it doesn't show actually the parabola that we are expected to see here. let me rerun the line. Okay, while we are waiting to see what's going to happen, then I think I can just move back to the R to show that on the R for you. Sometimes you saw that in the past also. Some of the plots which I had, it was not running on the R Studio. I do not know about why, but it was run into the R. I'm just going to do that into the R. But before that, I'm just going to go back to the slide which I had created for you on this one to make a highlights for you then, in order to finish our session today. Okay. Now, guys, look at this. The model which we created with the prediction, it gives a negative slope for the weight when it goes to the power 2, but the positive slope for the weight goes to the power 1. It means that, as you have seen, based on the polynomial sessions that we have seen in the past, it means that when the power of the weight goes to the power 2, the correlation between the heights and the weights which you have, it's going to be something in the opposite direction. Means that when the exponents to the weight is 2, the higher you become, you get weight, the shorter you look, or vice versa. The lighter that you get, the higher you look. However, the coefficients for the weight, when the weight is the power 1, is a positive one. You have seen that when we're talking about this, when we were talking at, I should say, at the instantaneous or average rate of change. Because these slopes are representing the average rate of change. But here is a positive. It means that when the power of the weight is 1, the relationship between the weight and the height is straight. It means that the heavier you get, the higher you become. Or the smaller you get, the shorter you get. This is the interpretation of the positive and the negative slopes of these variables that we have, that we talked about that extensively when we were talking about the instantaneous and the average rate of change. We saw that what do these stuff means then. Okay, that's essentially the thing which I wanted to talk about, the interpretation of the slope. But now if I come back to the slope, I come back to the R session that we had. Still the R is not run. When we come back from the break, I'm just going to run that for you onto the R to see that the fitted line that you get, it resembles like the parabola, which is going to be the plot of the polynomials of degree 2. This, I do not know why it's not run right now. I'm just going to do that a little bit later for you. But before we leave, I'm just going to give you a homework for you to do that as the fitting of the models that we have. I just want you now to think of what is going to be the difference if you have, let's say, a formula in your woman data sets that it shows the weight it shows the heights tilde weight to the power 1 plus I weight, which is going to go to the power 2 plus I, then weight is not going to the power 3. You see? Now, the fitting which we had, and of course you can just go with the data to the woman. I'm not going to run it now. I'm just going to leave that as a homework for you, that tomorrow in the lab session, we're going to talk about this. I'm just going to run now this model not on a quadratic functions. Now you are just going to fit your model on a cubic function, which is going to be a polynomial of degree 3. Please, when you are at home today, you run this model and do exactly as what we have done today on the previous model. Try to fit this exactly with the same codes which I have there. You are able to run it. I don't know what it happened on my the art studio. I didn't get run. To see that what you are going to get. You see that you are just going to get, I should say, different slopes and different coefficients and the different intercepts. And now I'm just going to do as a homework for you. You run that model for yourself and compare that to the quadratic and the linear model that we run that, I should say, on yesterday and the day before yesterday. It's going to become your homework that you're going to do that tonight. Then. Okay, guys.
Okay.
Awesome. Okay, this is going to be essentially our lab session today for, I should say, for the polynomial functions on in actions, I should say, to use that in the American woman. And now, guys, if you have any questions, I'm available to just answer that. Otherwise, I'm just going to stop the share and we can just go for the break now then. Let me stop the share. Okay, guys, any questions? You have been able to just run all the codes?
Maybe.
What, Laura?
We need to do the homework with R.
Yeah, with the R or R Studio. I know that you have the R, then R is totally fine if you just do that. It's only run the model as normally what we have been doing since last week and try to make a comparisons based on the things that we have learned between a cubic model, a quadratic model, and a linear model. And let me know tomorrow which model is the best one compared to the other ones.
Okay.
Okay. But any other questions? Everyone is fine?
Yes.
Sylvia, Anki, Jasper, Laura?
Yes.
Yes.
Okay. Fantastic. Then please, guys, don't forget about, I should say, the homework. Now we are just going to get, I should say, a couple of minutes break. Let me start the recording.